Let's take a look at a problem that has to do with efficiency. No machine in the real world is 100% efficient. And some of the energy that goes into these machines is lost to heat through various methods. In this particular problem, we have a gasoline engine that has an efficiency of 27%. It loses 800 joules to the radiator in the cooling system and exhaust in each cycle. How much work is done by this engine? Now, if you look at your formulas for efficiency, you'll notice that there really isn't one formula that we can use for this. We're going to have to use more than one. Let's begin like we always do, and we're going to start out by writing down the things that we know. We know that the efficiency of this engine is 27%. I'm going to write this as a decimal equivalent here. All right, and then we also know that the heat that is lost in this system is equal to 800 joules. So if this thing is only 27% efficient, that means that only 27% of the energy that's put into this system is going into making work. And that means that the other 73% is this lost heat. So if we look at our formulas for efficiency, you'll see that one of our formulas for efficiency is equal to 1 minus energy lost as heat divided by the energy that's added as heat. Okay, that tells us the efficiency. And in this particular case, we know the efficiency and we know the energy lost as heat. So that will allow us to find the energy added as heat. We're going to use that value to find ultimately the work that's done, but we need to know that one first. Let's go ahead and plug in our numbers, and we're going to do this without rearranging first. The first thing I'm going to do is I'm going to subtract 1 from both sides. What this is going to do is this is going to tell me that part that is being lost by heat, and that's going to be our value there, 0.73, and it's negative. Now we've got negative 800 joules divided by QH. Okay. Now we can multiply QH by both sides, on both sides, and then we can in turn divide by negative 0.73. So we're dividing by negative 0.73 on both sides. Let me write this out so it's a little bit easier to see. Energy added as heat is going to be equal to negative 800 joules divided by negative 0.73. Now you'll see that what this is actually doing is telling us a number. If 800 is what's lost, then what's a number that's going to give us what would be left for that 27% efficiency? So let's put these numbers into our trusty little calculator here. Now notice negative divided by negative, I don't have to deal with those. 800 divided by 0.73 gives me, oops, go back here, little calculator, a heat added of 1,096. We're going to round that to 1,096. So 1,096 joules of heat added. Now let me switch colors here so that you can see this more clearly. We're going to now look at another formula for efficiency, and this one says that efficiency is equal to the net work that's done. Oh, that's what I'm looking for. Divided by the energy added as heat. Added as heat. I don't know why I'm writing it this way, because I could do it a lot easier by writing Q sub H. All right. So this is our formula now. So efficiency is still 0.27 is equal to my work. Let's just use W net here. And my energy added as heat is 1096. So you can see that I can multiply 1096 on both sides. Pull out my trusty calculator here. While I'm doing this, is this number going to be greater than what I have for my energy added as heat, or is it going to be less than? Less than 290, rounds to 296, 296 joules of work is done by putting in this much heat energy, and that's because of our efficiency. We're losing a lot of it as heat. Okay, 296. Now, in the problem in your test, it has you rounded off to two significant figures. So if I was going to round this to two significant figures, what would this be? Well, that would round to 300 in this case. Or we could say 3.0 times 10 to the second, and that would give us a more accurate two places. Okay, so don't be confused by those rounding. Remember, we can only have the number of significant figures as the one that's least in our problem. And so in this one, we could actually only have one. This is our answer.